So, welcome to this WES Brokerage Event on Direct Generation. I'm Tim Hirsch, Managing Director of Wave Energy Scotland. I do recognise most of the people in the room, so there's quite a lot of knowledge of WES, but I'll just go through a little bit of an introduction to WES and a bit of a background as to why we're doing this.
Can we see the slides?
Yeah, if you can do the slides. I'm going to come to you, seeing as no one wants to sit at the front. Just to give you a bit of a background as to why we're doing this. And Jonathan will go through the detail of the design competition, and then we'll have the sort of the brokerage pitches after that. So that's the agenda for the day. If you're happy with that, let's just move on. Go on, Jonathan. So Wave Energy Scotland has been around for 9 years now. We started in 2014, and we were funded through the Scottish Government to develop or fund the development of cost-competitive wave energy devices. And to do that, we ran an innovation program based on competitive procurement for the last 9 years. 5 different programs within that, looking at power takeoff, looking at wave devices, advanced control systems, structural materials, and more recently, quick connection systems. You can't end my mic. Is that not working?
That's fine.
Oh, that was signaling that. So, and that has now really sort of come to an end now, the first stage of that program. And the real flagship program within that was the wave energy program, the wave devices. So if you just go to the next one. And you can see the 2 wave technologies that came through that program. We've got Simon from AWS here today. I don't think we've got anybody from Motion. But the program took a number of technologies, 8 technologies initially, from concept right through to proof of concept testing in real sea conditions. And it was Motion and AWS that came through that program. And now we're looking at the future and how we can, help those 2 companies to commercialize that technology and focus on what constitutes utility scale electricity. So, what is the best path for wave energy is the big question. If you just go to the next one, Jonathan. I just wanted to show some of these reports that have come out of Supergen, mainly done by the University of Edinburgh, that look at, well, what's the likely benefits in the future, the GVA that can be generated from wave energy, what's the likely deployment, what's the future look like? And a lot of the work has been based on the EU targets of £150 per megawatt hour, and the assumption that if we could do that by 2030, what would happen? And the brief summary of that is, well, if you can reach that sort of level of LCOE, the likely deployment in the UK of wave energy is about 6 gigawatts by 2050, which is quite significant. And the GVA associated with that is about £20 billion, which is great. That sounds great, but we've got to get to that starting point. That's the key thing. How do we get to that cost of energy? And you saw in the previous slides, perhaps one of the methods was looking at co-locating wind with wave. And WES has done a lot of work recently with OWC consultants looking at what the benefits are as if you can combine those together. And that's particularly significant for Scotland because ScotWind is such a large initiative, 25 gigawatts of wind, quite a lot of that on the west coast, quite a lot of that deployed as floating wind, but in an area where the wave regime is such that it's where we would like to put wave energy in the first place. So the opportunity of co-locating is great, and that may be a way to get down the cost curve. And the indications are that potentially 40% savings would be achievable if you could co-locate wind and wave together. So that is a strategy to get costs down. But as these reports all say, if we are going to get down the cost curve, large amounts of innovation are required, and radical innovation, not just optimizing what we've got, but looking at things differently. So co-locating with wind and wave, scaling as much as wave can scale is one method of doing that. And what are the other methods? And one of the things about looking at electroactive polymers and dielectric elastomers and DFGs is that it's a completely different way of converting mechanical energy into electrical energy, and has the potential of removing large parts of a WEC, and particularly that drive train that converts low frequency reciprocating motion into electrical energy, and potentially large cost savings. But the problem is we don't know enough about it, and that's really the reason why we're looking at a design competition and understanding more about what could be done with electrostatic generation. So I'll hand over to Jonathan to give you the details. Thank you.
Okay. Thanks, Tim. How's the sound for everyone? Would it help if I wore this and spoke with a microphone?
Oh, that's better, yeah.
Is that better? Okay. I'll do that. Okay, thank you, Tim. Thanks for the introduction. I'm going to talk to you about the concept of direct distributed flexible wave energy, which is something we've been investigating for a few years and now looking to try and build a strategy to push this technology forward. So I'll talk about high level about why we're doing that and what we're trying to achieve, what that strategy looks like. Then I'll go through some details of the call itself, the competition itself, which will repeat a lot of the detail that you've seen hopefully in the call guidance document, but will set us up for some questions which we can answer. We're wearing 2 microphones because we're recording the presentation so that we can share that on the website with everyone who wasn't able to join us today. And if we have questions and answers in the room, we'll write those down and we'll share those with everyone else as well to make sure everyone's got access to the same information. Okay, direct distributed flexible wave energy. So over the last 5 or 6 years, we've been supporting this technology and investigating its potential. It started with the power takeoff call, where we had a dielectric elastomer generator project, which went to stage 2 in our power takeoff call, but then due to its low level of maturity, wasn't able to compete with the more mature technology, so it didn't progress into stage 3. But we could see that there's potential as a future technology. So since then, we did a landscaping research project with Fraser Nash Consultancy to look across all of the alternative power conversion technologies, such as these electrostatic technologies, to identify all the options and down select those that might be promising. Then over the last 3.5 years, we have been co-supporting a PhD with the University of Edinburgh to do a similar thing, to look at what's the impact of radical innovation on cost of energy curves and the cost of supporting a wave energy technology or any other radical technology to commercialization. Then creating an evaluation process to look at these technologies specifically and compare them against the state of the art, and then using that evaluation process to identify these technologies again and score them using metrics and down select the 2 that we think are most promising, which in this case we've decided to focus on dielectric elastomer generators and dielectric fluid generators, which are examples of variable capacitance metamaterials. So we've got this demonstrator here, which was manufactured by 4C Design, John's over there, which you can all come and have a go at, but basically it illustrates the process of compressing a metamaterial, applying electrical charge to it, then relaxing it, and then harvesting that charge at a higher voltage, so you can extract more electrical energy than you put in. And that demonstrates the type of technology we're looking at in quite a generic way. So please do have a go at that, and we'll share a video of it for people who are watching this video back. So they're all examples of variable capacitance metamaterials which can be stretched, twisted, or bent to directly convert wave energy into electrical energy. And we think that could enable us to create a completely new class of wave energy converters. And I'll talk a bit more about the images that you've seen at the bottom there later. And to follow up in a bit more detail of what Tim said, we think this can have a really significant impact on new devices and on the levelized cost of energy of wave energy. If you look at the top image there, that gives you an outline of the cost centers of a conventional wave energy technology or wave energy system. So you've got the costs of moorings and foundations, the device structure, typically steel or concrete, then the steps within the mechanical electrical power conversion system, like a gearbox, and then an electrical generation subsystem, and then obviously the electrical connection. And there's a standard pie chart of standard contributions to LCOE on the right. But if you then replace that with a direct generation-based wave energy system, you can take that structure, power conversion system, and electrical generation subsystem and turn that into one metamaterial, which forms the device, the structure, and the power conversion process. So that's the goal we're looking for. A lot of these technologies have been and still are being demonstrated and tested as a retrofit into an existing wave energy converter, but we think that really misses the opportunity for big cost reductions if you still maintain the steel or concrete structure. And we think that can take us through to a big LCOE saving, and part of that project is to help us to try to quantify that better. Just to introduce how we're building a strategy around this, we want to get to the point where we can apply this technology to wave energy, but we're very aware that other sectors have really valuable applications for this type of technology as well, both as a generator, but also as a sensor, a transducer, or an actuator. And there's a lot of read across of the technologies and the enabling technologies within them that we can transfer between wave energy and other sectors, and we really want to build upon that opportunity. But we know there's a lot of enabling R&D required to get us to the point where we can realistically develop a wave energy converter. So what we want to do is drive the requirements for that by looking into the future, and that's exactly what this project is intended to do. So the Direct Generation Concept Design Competition is intended to design 5 concepts for wave energy converters, and by doing so, create a vision. This is what this technology might look like, and we can use that vision to illustrate it to government and to other sectors. It'll create a list of R&D requirements, so we know what's going to be needed to bring this technology forward, and it will demonstrate how this technology could compare to the current cohort of wave energy converters. So it's kind of looking into the future in order to drive the steps to get there. When we've got all of that information, we'll continue to try to build a cross-sector collaborative R&D program in these 3 key areas. So fundamental materials development and selection, metamaterial development, and the concept of a modular, flexible generator, which can almost be the building block of a new class of wave energy converter. And that's where we want to get to. So we're starting off with the Direct Generation Concept Design Competition, but then, as I'll explain later, we want to fill these different enabling R&D areas with other projects, whether they be in this sector or others. So onto the details of the competition. And as Tim said, after the competition, you'll all have the opportunity to share your quick pictures of your requirements and your capabilities. And then it's down to you to network and find opportunities to work together. So as I said, all the information I'll share here is in the call guidance document. And we've tried to boil it down into a clear objective of the project, which is to create completely novel direct generation wave energy converter concepts and create a development community that can champion a vision for a future of wave energy by quantifying the benefits and driving the enabling R&D required for their realization. So it's about creating that vision for the future, and it's about creating a group of people who can drive that. And what's that going to do to the Wave Energy Scotland strategy? As I said, it's going to give that vision, and that's going to help us to steer what program we can build around these technologies at the end of these projects. And that's all going to be dependent on how successfully we're able to design new concepts and quantify the benefits. So that out of that project, as I said, we're going to have lists of R&D requirements to help drive that early stage R&D, and that will help us to build that program and share those requirements with other sectors which might share those requirements. To drive that enabling R&D, it'll help us build upon funder collaborations. We've worked very closely with the Department of Energy in the States, and particularly the National Renewable Energy Lab, NREL, who have similar aspirations for this type of technology, but always a slightly different way of driving that R&D. And they've got a competition called In Deep at the moment, which is trying to drive a similar type of technology. So it enables us to share our knowledge, benefit from their knowledge, and build those cross-sector collaborations again. And really what we want to do is create a roadmap for how we get to the point where Wave Energy Scotland might be able to run a programme similar to the ones we've run before, where we directly support development of wave energy converters using this technology, if we can show that to be the right thing to do. So the project scope. Over the years, we've been evaluating projects that have been in development and evaluating the various characteristics and benefits and trying to narrow down on where we think the opportunity is. And we think that is to focus on cell-based or segmented modular direct generation subsystems. That's to say, there are lots of challenges with, for example, a dielectric elastomer generator membrane, which is going to be scaled up as a monolithic membrane up to a very large scale. There are many blockers in that kind of scale-up mechanism. So we think avoiding that by scaling up cells in number, by multiplying cells rather than the size of an individual cell, is a more promising route to go. And that is an appropriate route for both dielectric elastomer generators and dielectric fluid generators. We want to focus on using that multiplication concept to allow distribution of generation throughout the device. So instead of a large steel structure focusing very high forces onto a single central power takeoff system, that generation function is carried out by almost every part of a flexible device. And that allows us to follow the concept of minimizing the percentage of non-generating material components or cost and avoiding high-cost materials like steel. And that takes us probably towards the use of flexible materials for the majority of the device. So that's the scope that we've proposed. The call format, as hopefully you all know, we've taken a slightly different approach to previous WES calls, where in order to get interest from other sectors and as wide a group of people as possible, we've introduced a pre-proposal, which is quite a short form, response form, and it focuses on the building of a team and the understanding of the challenge, understanding the requirements. And we will take forward up to 15 proposals and invite them to submit a Part 2 proposal. In that full proposal, the focus will get onto the concept and project outline, the team building, and how are you going to go forward and develop a concept and respond to the specific requirements. And that will lead to up to 5 projects being selected from those full proposals. We expect the projects to take about 12 to 14 weeks. So that would be completing towards the end of January 2024. And in the call guidance document, you'll see a very clear list of specified outcomes from what we expect a project to deliver and specific outputs, physical outputs. And we don't want that to be the end of our support of direct generation. We want to take up to 2 project teams forward towards a technology development program, a full technology development program. And the format of that will evolve as the projects evolve and the other things that we're supporting evolve. So we need to be able to demonstrate a benefit, identify those R&D requirements, and we will work to build the funding opportunity to support that. So we have a total budget available of £250,000, and we will select up to 5 projects of up to £50,000 each, which will be funded by a grant mechanism at up to 100% of eligible costs. And in order to ease the delivery of that, up to 50% of the total cost can be paid on submission of an interim deliverable, and then final payment, like the rest of the WES programs, on delivery of the final outputs. Eligibility and the evaluation process. So we would like proposals from teams led by a UK registered organisation, and at least 50% of the R&D effort to be carried out in the UK. But partners, advisors, any other kind of contributions to a team are welcome from the UK, EU, European Free Trade Area, or the USA. And in the call guidance document and the response form, you'll see how they will be evaluated, how they'll be scored, how the scores will be weighted, and those will be evaluated by a Wave Energy Scotland team of 3 or 4 people. Okay, and just a little bit about teams. As I said at the beginning, I think there's a really strong opportunity for the requirements that come out of this project to overlap with those from other sectors, whether they be actuators, whether they be flexible electrodes, the fatigue life of the elastomers and those electrodes, bonding of membranes to each other, self-healing opportunities, and then some of the other characteristics listed on the right there. And those are going to be cross-sector requirements. So good teams might bring together knowledge and know-how from wave energy technology and experience of the ocean environment. Applications such as soft robotics, development of electroactive polymers themselves or other electrostatic actuators and generators, wide application of flexible materials and electronics, and also the manufacturing processes. And I think that manufacturing process is quite a key part, because we need to ensure that at this very early stage, when we're driving R&D requirements, we try to make decisions that make the technology we develop compatible with low-cost mass production techniques, and also compatible with environmental acceptability. So teams should be quite broad in the skills that they bring together. And we've tried to provide some concept inspiration. Again, we carried out a series of workshops with the WES team and 4C Design to be able to come up with some concepts that we could use to propose to the sector to gain interest, to say this is what we think it could like, but immediately to have people question them and therefore be able to come up with better solutions. So we came up with a range of solutions, and these are the types of questions we were asking ourselves when we tried to create these solutions. So first of all, how does the device capture power through hydrodynamic interaction? What provides the opposing reaction and restoring force? Does the device change volume or shape? And what physical device, module, and metamaterial characteristics are required to deliver that shape or volume change and realize that device hydrodynamic interaction? So trying to kind of think all the way down to the bottom level of what is this thing going to be made out of, right up to the top level of how does that interact with movement of ocean waves. And those are 4 examples which operate in different degrees of freedom, which exercise the materials they're made out of in slightly different ways, and start to ask those questions. And hopefully people will start to look at those and immediately ask questions or pick holes in those concepts, and it will lead to different ideas in your minds of ways to create that interaction between waves and the metamaterial that the device is made out of. And then just back to the collaborative R&D strategy. I said that we're launching this concept design competition so that we can try and send the R&D requirements and the benefit and the vision back into the enabling R&D. And now we're starting to fill those stages of enabling R&D with other projects. And the first example is going to be launched next week, which is a flexible fund from the new Supergen Offshore Renewable Energy Impact Hub. And we're going to fund a project on concept design and experimental demonstration of a dielectric elastomer or dielectric fluid generator concept, where we hope that project will be able to demonstrate a multi-cell solution in laboratory conditions. So that's just the first example of filling one of these boxes with an enabling R&D project. And as I said, we want to fill the other boxes as well with either wave energy specific projects or projects with similar requirements in other sectors. And as I said, your projects would start to be able to build those links with other sectors by demonstrating the opportunity.